Okay, now we're going to discuss why we study probability and statistics. And in a nutshell, the reason we study probability and statistics as part of our curriculum is because probability theory is the logic of science and engineering. And the reason I say that is because all natural events are random, and information by definition is non-deterministic. Otherwise, if we hear something we already know, it wouldn't contain any information. Systems are also subject to natural events, and therefore systems, as a consequence, are random. So whether we talk about natural events, the information we share, or the systems we design and analyze, all of them involve randomness. And understanding our systems and understanding nature requires us to understand the likelihood with which events happen, the likelihood with which our system is subject to external inputs or internal results, and the nature of information itself. All of that requires knowing about the likelihood or probability of things. So, again, the information we receive, exchange, and provide in a system is random. And the events that modify the behavior of the components of our system are also random. And then what we have is that we need ways to reason in some quantitative ways about these likelihoods with which events take place. And we need to be able to predict the behavior of the system or the components of the system. And we need to reason about the data that we have, and in some cases in large quantities. And we need to do that using meaningful samples, and we need to understand what meaningful samples mean. And we need to make predictions based on our samples of large quantities of data. All of that involves probability and statistics. So statistics can be said to be the art of extracting information from data, in that the collection, presentation, analysis, and use of data to make decisions and solve problems is what we need to do with the data we collect. And information is presented to us from the data we receive, and we need to draw conclusions from that information we extract from the data. And there are many statistical methods that do not involve probability, and but as a consequence may result from random experiments and processes. Then what about statistics? Well, statistics can be viewed as the art of extracting information from data, and the collection, presentation, analysis, and use of data to make decisions and solve problems is all the whole reason why we study statistics. And if you think about it, information is presented to us in the form of data, and we need to draw conclusions from the information we have obtained from the data. And there are many statistical methods that do not involve probability, but yet the data that we have results from random experiments and processes. So statistical reasoning based on probability theory provides strength to the analysis and predictions that we need to do in statistics. Together, probability and statistics help us map data to information through mathematical modeling of the random experiments. So statistics goes one in hand with probability theory. There's a large number of applications of probability and statistics. I just mentioned a few that pertain to computer science, computer engineering, electrical engineering, and robotics. And so you can see that chances are that you will see some of the areas in which you're interested in the list that I provide in this slide. And we will be focusing on a number of problems that pertain to networking, a very few in robotics, and as time permits, in some other fields of research. But hopefully after this course you will be able to apply what you have learned in your particular area of interest. I bring this beautiful picture of the Aloha Tower in downtown Honolulu, as well as Waikiki Beach, which is about 15 minutes away from the Manoa campus of the University of Hawaii, because that was the place where one of the main results in wireless networking based on the application of probability theory started. Case in point is the Aloha system. In around 1973, in late 60s, early 70s, Abramson and Kuo developed the Aloha system based in Honolulu, and they introduced the notion of packet switching in radio channels. Believe it or not, at the time there was no such thing as Wi-Fi, and what they came up with, in particular what Norm Abramson developed, was a beautiful mathematical model that predicted the behavior of this Aloha system that we will discuss subsequently in the course. And he came up with this very simple formula relating what is called the throughput, or the useful information in the system, to the total offered load in the system. And that result was published in the early 70s, and it was for me one of the my motivation to attend the University of Hawaii. But for the rest of the world, they opened many questions that produce large amounts of research and commercial products. Examples of such questions is how do we derive the result on the throughput of the Aloha system or more complex systems? And Abramson derived the simplest model for Aloha, and by doing this very simple model set the stage for a plethora of research papers in the following 40 plus years since the introduction of Aloha. Questions that still remain with us are how and whether we can do better than Aloha under different conditions, and the Wi-Fi that we enjoy today, and in fact wireless internetworking today, are all due to the introduction of the Aloha system. Other type of questions that engineers and scientists ask themselves is what is the best multiple access that we can do under some conditions, and how do we go about modeling the performance of a large computer network that doesn't have to be as simple as the Aloha system, but it can be really complex like the internet at large, and how accurate those our models have to be useful to us. The more complex the model is, the more difficult the math becomes, and the harder the questions become, and chances are at some point we are not able to solve the problem. So by necessity we have to have simple models of the system. The question is, how accurate do we have to be to keep the modeling simple and yet the results useful? Another networking example is the internet itself. You may know that the internet operates with what is called packet switching, and the question is, why is the internet based on packet switching? Before the internet became the way to communicate throughout the world, people used to just simply use the telephone system, which was based with circuit switching. And with circuit switching, it used to be the case that the physical resources from a source all the way to the destination were reserved for the duration of the telephone call, and then data was exchange on these physical resources, and then the call will be terminated. But then in the late 60s, early 70s, the Department of Defense decided that the old circuit switching method for sharing communication and processing resources wasn't good enough for large-scale purposes. So they funded the development of packet switching, which is based, as we will see, on the concept of statistical multiplexing. And what is very different from between packet switching and circuit switching is that with packet switching, what we have in the network are switches that are able to take information from multiple telephone call equivalents and mix them up based on the statistical behavior of the users and use the resources in a much more efficient manner. All of these, or the main concepts behind this comparison between circuit and packet switching was to a large extent due to Len Kleinrock, now a professor at UCLA. At the time, he was a PhD student at MIT, and in his PhD thesis, he took a look at the way what we call now packet switching operates, and used stochastic modeling to describe the behavior of packet switching in multi-hop computer networks. Notice that work was in the mid-60s, so it goes hand in hand with the development of the Aloha system. So we will come back to these kind of questions as to why we do packet switching, and how can we show that the internet is necessarily better than the old telephone system. That's one the type of questions we can answer using probability theory. Another example is the way we do robotics today. Now we have robots in our household. Maybe you have a Roomba robot, or you may see some unmanned aerial vehicles, or you may see all these unmanned cars in the highway, or you see robots in factories, or you see robots in many other places. And all of these robots, whether they are at home, or in the factory, or in the air, or on the streets, or in stores, each of these robots have to sense their own state. They have to sense the environment. They have to take some actions, so like move or avoid obstacles, and they have to communicate at the very least with the entity, usually a human, who is controlling the robot. And all of these necessarily involve probability and statistics. More and more also we are mixing robots with networks, and hence now we talk about cyber-physical systems and cyber-physical networks, and we may have flying robots that communicate with the ground and with other aerial vehicles and with people, and all together they try to accomplish some mission. And so these drones may be tasked to carry out some actions, and they will be able to do certain actions by themselves based on what they sense and what they communicate with one another. And again, all of these cyber-physical networks involve sensing, actuating, communicating, and coordinating among robots, and between robots and humans, and between robots and other computer networks.